Okay, so here we go, real quick. You guys, please tell me.
Yeah, so you can just wear this.
Thank you. You tell me, do you want to go through, and I'll kind of leave this up to you. I would normally definitely do this, but being as we want to get to the lab, you can answer this for me. Are you okay, you think, without, or do you want to do another example of using the limit of the difference quotient to take a derivative?
Can we do one more?
Sure, yeah, but we definitely can't. Remember, I think that's probably a good idea. And then the other thing, real quickly, I just want to give you a couple rules for derivatives. And then we'll head on down there. I want to make this, don't let me do this too long, though. Well, I tell you what, when we get to, if it gets to like 8:20 or near it, tell me to be quiet. Yeah, give me that. Give me this, and we'll head out. But I think we'll be fine. Okay, so let's look at this. How about, what if we have, the function f of x equals 1 minus x squared, and I want you to find for me, how about, find the equation of the tangent line at x equals 2, okay, using the derivative. Now let's kind of at least get started on this together, and then maybe I'll let you work in groups for just a second here and see if you can get through this a little bit. But what did we say that the definition of the derivative was? And remember, the derivatives, we're calling this, and we'll talk a lot more about it, but you have the basics right now. The derivative is the slope of a curve, or the slope of a tangent line to a curve, right? And we wrote it, this is the notation for now that we're just going to stick with. There are other notations later that, like I say, we'll introduce. Remember what that formula was, though? What the definition of a derivative was. And it's a limit, right? Remember it? And what you want to think of here is that picture we drew yesterday. And in fact, I've got that here. Let me go back a little bit. We did live stream. There it is, right? Here's the picture, right? We're taking the limit of the slope of the blue line, the average rate of change, slope of a secant line, as we migrate these 2 points together into a tangent line, right? And remember, we defined this in terms of some point x, f of x, and some other point that's an arbitrary distance delta x away on the x-axis, right? So how did we define the slope of a secant line in terms of these 2 points, x, f of x, and x plus delta x, f of x plus delta x? And this is no different than what you've been doing for years and years. What's the slope?
F plus delta x.
Yeah. Okay, delta y over delta x. So good that the f value at the or the y value at the second point, value of the function, minus the y value at the first point, change in y, over delta x. That's what we're calling the change in x, right? And so, just looked like that, didn't it, right? That's what you're saying. Okay. And so that's the slope of the secant line. And then to make that a tangent, what did we do? We used kind of some mathematical magic. We said we took a limit as what happened? What goes to 0? Delta x, yeah. And that effectively just took this point and pulled it back on top of the other one, right? Made them into a single point. Okay, so that's what we always start with then. Remember, we want to start with the general definition of a derivative. Start of every problem would be the same. The limit of f of x plus delta x minus f of x over delta x as delta x approaches 0. And then we get specific. We start with the absolutely general, and then we plug in the specifics of our process. So we've got a specific function, and eventually we've got a specific value of x that we're going to evaluate our derivative at. But for now, we need to apply the general derivative definition with this function. So how am I going to do that? Yeah. Okay. We'll just do this together. You guys can just kind of inform my steps here. So then what is this part? Oops, thank you. about this part right here? What's that gonna look like for our function? If f of x is 1 minus x squared, what's f of hand? 1 minus hand squared, right? Hand could be, in this case, hand is the quantity x plus delta x, right? So we get 1 minus hand squared, right? Minus f of x, we already know that's just the quantity 1 minus x squared, right? All divided by delta x. Delta x goes to 0. Okay, so now, what's going to happen here? Just anticipate here a little bit. Kind of be thinking forward. How are we going to resolve this problem of indeterminacy?
That doesn't cancel.
Okay, we're going to cancel the factors that are causing the 0 over 0, but we know what those are going to be. The 0 on the bottom is a delta x, so the factor that gets canceled on the top is going to have to be delta x. And that's, you know, sometimes you might think, well, gosh, it always will work. It's always going to work if the function is differentiable, and we'll get to that in just a second. It's always going to work out in such a way that all of the naked terms without delta x's are going to cancel by addition. And then we can factor out a delta x and cancel vertically. It's always going to be that way. So you know the strategy. It's just a matter of executing it. So then, just doing the algebra here. You guys are good at algebra. And the research shows it's good to do mental math with algebra. Doing mental math and doing algebra recruit the same neural connections. So I'm going to force you to do that a little bit in here. And you should do it on your own. See if you can take this and simplify that in your head. Think about that a little bit. Turn it around, and what's that going to be? If I want to take all this red stuff and just turn it into a sum of terms. I'm going to get a 1. Good. Minus, right? Minus x squared. Okay.
Minus 2x delta x.
Okay, and I'm subtracting a quantity, so let's go ahead and just distribute the negative sign.
Yeah.
Does that make sense?
Yeah.
Minus
2x delta x. Minus delta x squared.
Very good. Okay. And then over here, I'm just going to distribute the negative sign. Minus 1. Good. And all over, and this is a limit. Delta x. Okay, so horizontal cancellation. And you understand what I mean by that when I say horizontal cancellation? Horizontal cancellation is when stuff is just adding to 0. In other words, cancellation by addition. Okay, so these go to 0 and we can get rid of them completely.
The 1s and x squareds.
The x squareds and the 1s. Okay, and as advertised, look, both of the terms remaining have delta x's in them, right? And so, what can we do?
Factor x.
Okay. I can pull out a delta x. If I pull out a delta x, there were a couple questions about this. Now, what am I left with? Now, I'm going to remind you that factoring is a process of division. You can always think of factoring out a greatest common factor as undistributing that factor. Okay. Good. So if I undistribute a delta x, I'm left with a negative 2x in the first term, and here, minus delta x. Over delta x. Questions on that?
No. Got
Okay. And then we can cancel vertically here. Now, canceling vertically, are they canceling to 0?
it.
To 1. They cancel the 0 horizontally to 1 vertically. Okay, so that's a 1 on the bottom. And now we can take our limit, right? Okay. So this guy right here, and our limit goes to 0. Make sense? And we're left with what?
Negative 2x.
Negative 2x, and that is huge. Now we get a function out of this. It's not a specific answer. This is the derivative function. Its job is to tell us the slope of the tangent line for any value of x we choose on our functions. Very powerful, okay? So, we got the derivative function, but remember our goal really was to find the equation of the tangent line at x equals 2. Okay, so what are the two ingredients for a line?
Slope and point.
Slope and a point, okay? Let's get the point first, how about? If x, we're trying to find the equation of the line at x equals 2. Remember, our function, I think, was just, what was it, 1 minus x squared. So, how am I gonna find the y value? Yeah, I'm going to, and really the terminology would be we're gonna evaluate the function at x equals 2. Yeah, and we'd write that as f of what? F of 2, yeah. And does that make sense when we say that? F of 2 means this is the functional value when the input is 2. What are we gonna get?
-3.
-3. Okay, which tells us that this is the point. 2, -3, right?
Mm-hmm.
Okay,
Yep, totally see it.
makes sense?
Got it.
Okay, so then the slope of the tangent line, how am I gonna get that? Evaluate what? Okay, good, evaluate the derivative, or f prime, at 2 also, right? So that's gonna be f prime of 2, which is -4? So we got a slope of -4, we got the point 2, -3. Now we just do a little algebra 1. All right, so real quickly, how do we do that?
Equals.
Slope-intercept, sure.
Yeah.
So this is what we want to end up with.
Y equals
-4x plus b, good. And to find b, what could I do? Okay, and that makes sense, right? Because plugging a point in, if the point is on the line, remember, and this is a big deal. I mean, I'm sure you get this, but I want to just say it so you make sure these connections are real solid. If a point is on a line, then that means that the coordinates of that point are solutions of the equation. In other words, they satisfy the original equation, right? So I know if I plug these in, it's going to work. It's going to yield a true, a true statement. So I get -3 equals -4 times 2 plus b. So what's b? What is that? 5, okay, so b is 5. And there are my ingredients. B is 5, m is -4, so y equals -4x plus 5. How about that? Good stuff, huh?
Victory.
Okay. All right, so we'll talk more about this, and I'm going to draw you some funky pictures on Monday or Tuesday. We'll get into much more detail with this. But for now, I just want to give you some rules about where derivatives exist. Okay, so this is called differentiability. Differentiation is the process of taking derivatives. Okay, so that's what we talked about. Differential calculus. That's the calculus. Differential is an adjective, which is saying it's the calculus of doing this, taking derivatives, right? And so the word differentiability is like take the something like that. Take the derivative ability. Can you do it? Does the derivative exist, right? So wherever the function is differentiable, we can take a derivative. At places where the function is not differentiable, the derivative wouldn't exist. So where are the places where derivatives don't exist? Okay, here they are. And this first one, once again, just so we can get to the lab, I'm going to kind of give you this stuff to work on the problem set with. We'll look at an example of a function, of maybe a step function on Monday, and kind of talk about, well, why is this? I'll give you a brief answer now, but we can maybe have a better answer later. Breaks in the function. are breaks in the function are places where the derivatives don't exist. And the reason for that, if you think about it, if we think about these ants, well, if we think about the definition of a derivative, I can just give you a really, really quick, probably not completely satisfying reason for that. What's better than nothing, maybe? Now, what if instead of a nice connected continuous function there was a big break in it, right? Well, let's say that the break occurred right at the point where we're trying to seek the slope of the tangent line. If I were to move to the right any distance delta x, I'm going to take this discrete jump in the function, and my change in y is never going to shrink to 0, is it? As delta x shrinks backwards, there's always going to be this big delta y on top. And eventually, that difference quotient is going to look like some number divided by 0, which is undefined. Does that make sense? I mean, and we'll look at that in a little more detail, but you know that in those situations where you approach the break in the function, and really this is just the picture we need, I guess, if this is our function. As the ant is right here, let's say, if the ant's right here, and delta x takes us up to this second point up here, as this point migrates back, there's always going to be this big jump, delta y, no matter how small delta x gets, right? So qualitatively, that's an explanation. So breaks in the function. Okay, here's maybe another one that you might expect, I guess, is places where you get vertical tangent lines. And that makes sense too if you think about it. Because if derivative is slope and the tangent line is vertical, what's the slope of a vertical line?
0.
No,
Undefined.
Undefined. Horizontal line has 0 slope. Vertical line is what we always have said is no slope or undefined, right? And so therefore that's a natural connection that the derivative would have to be undefined there because you can't even define a slope, right? Okay, here's the one that maybe is a little strange. Sharp corners. Which we call cusps. Sharp corners are places where derivatives aren't defined. And we'll, once again, we'll talk more about that soon, but I can give you just a real brief explanation of that right now. We have something like that. At this point right here, now think about this. If we define the derivative as small changes in delta y over delta x, if I look at those changes from the left, what they essentially translate to is a new sense developing for our calculus ants. Calculus ants, as they walk along a line, they have now evolved not only the ability to know their coordinates on the xy plane, they also know the slope of the line. They can sense the slope of the line as they take these steps, right? And that corresponds to just little steps of horizontal distance delta x and vertical distance delta y, and we're just shrinking those down as delta x approaches 0. Does that make sense? But they kind of get a real sense of what the slope is. We'll make this a non-ant, more mathematical discussion next week, but for now, as an ant approaches from the left, as he approaches this point, isn't he seeing some, fairly large positive slope? That's what his slope sensor is saying. Agreed? As he steps onto that point. Because isn't slope really slope has to be defined not by a single point, but by the relationship between that point and the points around it. Does that make sense? Okay, what about an ant coming from the other side? This is kind of wacky green ant. As he's coming backwards along here, his slope sensor is reading this slope. Okay? But how can you have multiple slopes at the same point? Obviously you can't, right? Those two slopes, in order for this thing to have a slope at that point, ants approaching from both sides, their slope sensors would have to read the same value. And they don't here, okay? And once again, we'll look at that in terms of limits, and there's a way you can show that pretty easily. But for now, that's a pretty good way to qualitatively think about it. The slope sensors don't agree, and so there is no slope. Okay, so sharp corners are places where derivatives don't exist. And so this introduces a really cool word in math that is a loaded word. Yes, ma'am?
Did they twine
What's 820? Okay, we gotta go. Here's the word. I'll give you, yeah, there you go, good. I'll give you the word and we'll head out. The word is called smoothness. Okay, so here's what we say. We say that a function is smooth, and that's such a great word, because it's exactly what it looks like. Smooth equals continuous plus differentiable. This function is continuous, right?
Yeah.
But it's not differentiable.
No.
Because there's a sudden change in the slope. And so think about it this way, if I were to rub my hand over it, it would feel jagged. If a function is gonna feel jagged because it's got cusps, it's not smooth, it's not differentiable. So continuous, continuity, and differentiability combined mean nice, well-behaved function, smooth function, where the derivative is always defined. Okay? We'll get back to that. Let's go down to, I think, 205.